In this video, we want to continue our study of secondary surveillance radar. In particular, we want to look at what's called Mode S responses, or the Mode S system. So we'll review the learning outcomes. We'll look at the primary and secondary surveillance radar concepts. We'll look at secondary surveillance radar modes A and C. And then we'll have some new stuff, so discussions of some issues with mode A and C. And mode S as a solution to some of these problems. So what do the interrogations in mode S look like? What do the responses in mode S look like? And then we'll talk about the concept of Squitter and extended Squitter, which are technologies that allow us to implement what's called automatic dependent surveillance broadcast, where the aircraft will send its position and velocity information out to the rest of the world. We'll then have a summary and talk about what's coming next. So the learning outcomes for this module, to remind you, are that when we get done, you should be able to tell the difference between primary and secondary surveillance radar. You should be able to describe the principles of Mode A and Mode C secondary surveillance radar operation. You should state how the data in Mode A and C are encoded. You should be able to describe the concepts of Mode S operation and how the data in Mode S interrogations and responses are encoded. And then you should be able to talk about how ADS-B is implemented using secondary surveillance radar, or Mode S, extended Squitter, actually. So we saw both primary and secondary surveillance radar last time. Primary surveillance radar we saw required more power because of the way the reflection also acts like a point source. So the antenna acts like a point source, the reflection acts like a point source. So the response falls off like the fourth power of the distance to the aircraft. And so you really have to transmit a lot of power. We saw it on the sort of megawatt scales. The secondary surveillance radar doesn't have to transmit as much power because it only has to get out to the aircraft, and the aircraft is going to respond on its own, responding to the interrogations. These are both ground-based systems, and we saw on the chart to the right, the ASR9s and the ASR11s are the primary surveillance radars, which almost always have a secondary surveillance radar site attached to them. So secondary surveillance radar, also called ATCRABs, Air Traffic Control Radar Beacon System. Mode A and C were encoded. The interrogation comes in from the ground to the aircraft on a 1030 megahertz carrier. The aircraft responds on 1090 megahertz. And we saw these Mode A, Mode C interrogation modes that were indicated by the way these pulses came in, the pulse 1 and pulse 3, the time between pulse 1 and pulse 3 told us whether it was a mode A or a mode C interrogation, and the fact that whether P2 was smaller than P1 and P3 or larger. P2 came from that omnidirectional set of antennas, and so if P2 was larger, that means you were not in the primary beam of the rotating antenna, and so you were supposed to not respond if P2 is larger than P1 and P3. So we saw in mode A that the response encoded the identity of the aircraft, encoded as a 4-octal digit code, the squawk code. And so the bits, the digits A, B, C, D there are encoded in a binary coded octal there. So you have 3 bits, 1, 2, and 4, the least significant to the most significant bit for each of those digits there. And so those were presented in this bit stream there in an interleaved way. So you had a framing bit, then you had the least significant bit of the C, and you had the least significant bit of A, the middle bit of C, the middle bit of A, and then the most significant bit of C, and the most significant bit of 4, a 1 pulse pause, and then you did the same thing with the B and the D numbers. Finally, you had a final framing pulse. There's also an identity pulse that could be transmitted if the air traffic control asks the pilot in command to turn on the identity system, and that'll make the aircraft stand out on the controller screen. The mode C response was like the mode A response, and then it was followed with a second word, which was altitude encoded as flight level. So it's kind of funny how it did it all, because it used the D, A, and B digits to represent a 500-foot increment of the altitude, and then the final 100-foot precision was coded in the C using 5 of the C possible codes there. And these are all done as what's called gray codes. So both the 500-foot increment altitude is encoded as a gray code, and the 100-foot increment is encoded as a segment of the gray code, 3-bit 8 gray code there. Gray code where it only changes from one increment to the next by a single bit change. So the final version of the altitude is minus 1,000 feet plus this number encoded in the D, A, and B bits, digits, times 500, and then the number encoded in the C digits, which is going to be from minus 200 to plus 200. Okay, some issues with mode A and C, just your basic transponder operation. One is what's called fruit, false replies from unsynchronized interrogator transmissions. So in the diagram to the right, there's the aircraft. The lower right is the interrogating ground station. And so you can see its beam going out there. But there's also a nearby another interrogating ground station. Its rotation is in a different phase. It's going out a different direction. And so the aircraft is not being interrogated by the second ground station. And yet the response from the aircraft is going out to both ground stations. So that's called fruit, false replies from unsynchronized interrogator transmissions. So again, because the interrogation is directional, the aircraft is only getting interrogated by the one station, but the response is omnidirectional, and so the response is received by more than one. So the ground station processing has to include what's called defruiting, which is to clean up those non-interrogations that responses come in the replies that weren't the responses from this ground station. The other another issue is called synchronized garbling. So in synchronized garbling, now you have multiple aircraft inside the interrogation beam from a single ground station. I mean, at the distance, 60, 100 miles out, the beam width there can be a couple miles wide. So it's easy to get multiple aircraft, especially at different altitudes and at different radial distances from the ground station within the beam. And so multiple aircraft respond, but the responses can't be distinguished because they're coming back and they're overlapping. And so this is, again, synchronized garbling. So if we reduce the pulse repetition frequency, traditionally in primary radar, 20 to 30 pulses a second, reduce it down to say 4 to 8 pulses, or excuse, pulses per scan, down to 4 to 8 pulses per scan, then there's going to be both fewer responses, and so it's easier to defruit because you can tell which ones come from your own ground station, and also less synchronized garbling just because you have fewer interrogations. Another issue is the number of addresses. I mean, we've only got 4 octal digits here, and that's just 4,096 addresses. And so we'd like to be able to address additional aircraft. And so because the responses, I mean, all the aircraft, on a single sweep, all the aircraft within range from a ground station respond every sweep, and maybe multiple times within the sweep, again, depending on how many pings there are. It makes there's no way to address individual aircraft. So all this just comes back to the ground, to the radar at the air traffic controller, and they can get, again, the identity of the aircraft is coming back from the mode A and the mode C responses, and yet there's only so many you can have, and there's no way to ask us individual aircraft particular questions. This is addressed through mode S. So mode S, or selective or select, enables the aircraft to the air traffic controller to talk to an individual aircraft, and it's backwards compatible with mode A and C. So here we see the original mode A and C interrogation, P1 and P3, with P2 transmitted by the omnidirectional antenna encoding this. So mode S adds a mode P4. And this will be ignored by transponders that only have mode A and C. Those are now obsoleted anyway. All instrument flight rule aircraft have to have a mode S transponder. So there's a second, another pulse here, P4, which is either 8/10 of a second, 8/10 of a microsecond wide, or 1.6 microseconds wide. So again, if we just in the when it's 8 tenths of a microsecond wide, 800 nanoseconds wide, that's just a standard mode A or C interrogation, and the aircraft will respond as it would with a mode A or C interrogation. When P2, there's a bug here on this slide that P2 is actually transmitted by the directional beam for this all call response. Excuse me, no, P2 is still sent by the Omni antennas for the all call, but P4 is now a 1.6 microsecond long pulse. That's the mode S all call. So it's sending the air traffic controller is sending out to every aircraft saying, give me your identity. So each aircraft will respond. We'll talk about the responses here in a second with its unique 24-bit identity, which is assigned by ICAO, which is the International Coordinating Organization for Aviation. Uh, and once the aircraft responds to this all call and sends its address back to the aircraft, to the ground station, then it locks itself out from any further all call interrogations for 18 seconds. The selective call, this is when P2 is transmitted by the main directional antenna. The selective call is when the ATC is addressing the individual aircraft. So now P2 is transmitted by the directional antenna, and then P6 is going to be this compound pulse here, which starts with a 1.25 microsecond pulse. And then that's followed, there's a synchronization that happens in the transition of this next 0.5 microsecond framing pulse, which will have one of these phase shifts, which is, this is going to be encoded using what's called binary phase shift keying. Just to correct what's in some of the reading, the P6 pulse starts 3.5 microseconds after P1. So this interrogation is encoding encoded using what's I mentioned as phase shift key. So in phase shift key, each of these 0.5, half a microsecond pulses there that consist of the interrogation, excuse me, a quarter of a microsecond pulse, 0.25 micro, consisting of the interrogation. So you have this 56 or 112-bit data, the interrogation itself, which is framed by these half a microsecond pulses. And again, so this is encoded using what's called binary phase shift key. And in this framing of binary phase shift key, when you have a 1 as your next bit, then you have 180, you just do an SIGN change from plus to minus or from minus to plus. When you don't have a phase reversal, then that's a 0. So the interrogation is encoded in the first 5 bits of the message. And then you have the 24-bit address going out, and then you have 24 bits of parity. And then there's an extra bit there to get to the 56 bits in the interrogation. Or you can use a long, and the longer interrogation will code some of these other responses here. So the aircraft's going to respond on 1090 megahertz. It responds in a different, using a different system. There's this preamble 8 microseconds. That's just going to be your pulse amplitude modulation. We're just going to turn the 1090 on and off using these pulses. So they're half a microsecond long. There's a space of 1 microsecond after the first one. And then there's another 2.5 microseconds or 2 microseconds. And then you have the second pair of pulses spaced the same way. And then the whole thing is 8 microseconds long. And then you get the data coming that the aircraft is transmitting, which is either going to be 56 or 112 bits. And these are encoded in 1 microsecond slots using what's called pulse position modulation. So in pulse position modulation, if the first half of that 1 microsecond is turned on, that's a 1. And if the second half is turned on, that's a 0. So it's a different encoding scheme than used on the interrogation, which was using phase shift key. And the message here, again, we have 56 bits initially, and there's going to be an 8-bit code. I said you had an extra bit left over in the interrogation. Actually, you have 3 extra bits left over for the could be used. Then you have 24 bits, which is your aircraft ID, and then you have 24 parity bits for the whole message. So you can also send the a 112-bit message, and then you would have an additional 56 bits where the aircraft can reply with its altitude encoded in what's now a 25-foot resolution, or can reply to other coded features, particularly in the same way that we'll see with the Squitter and extended Squitter in the next couple of slides. So Squitter is the aircraft responding to nothing. Once a second, the aircraft sends out its identification to everybody as if it was replying to an interrogation request. And so the Squitter response is going to have an 8-bit, you can have the same preamble, and then you can have 8 bits to say what this message is, and then 24 bits to say what the aircraft address is, and then 24 bits of parity. So we've got these we can also use 112-bit data blocks, and that gives us what's called extended Squitter, where again, there's going to be a identifying 8 bits to say what this block consists of, and then you have the aircraft address, and then you have a 56-bit message, which could include the altitude, location, velocity, and then you have 24 parity bits. So the coding here, you can see some of the different codes that can be sent back. So we can see the altitude, information about the aircraft, which antenna we're using. We can say information about velocity, whether we're going north, south, east, west, vertical rate of climb, and the like. So there's a lot of different information that now can be put into that 112-bit message. But we won't get down to the details of that. We just want to identify that the fact we can encode the location and the altitude, and the aircraft is sending this out to everybody. Basically, this is the idea of what's called automatic dependent surveillance broadcast over Mode S extended Squitter. So the aircraft is receiving the GPS information from GPS satellites. It has figured out where it is using GPS, and now that it has its information of where it is, it can put that into the 56-bit message there for ADS-B with location. It can also put the velocity and the like. And so this information can go both to ground, to the ground control, and it can also go out to other aircraft. So other aircraft can use this information. This information can also be used for collision avoidance. So the TAWS system uses ADS-B, excuse me, uses extended Squitter to communicate location. I mean, uses this information of location coming in to decide if it's too close to another aircraft. So ADS-B is automatic because the pilot doesn't have to do anything. It just sits there once a second sending out location and other kinds of information. It's dependent though because it's not its own source of information. So you have to have GPS or inertial navigation, some way that the aircraft has to determine its own location. It's useful for surveillance. That's what we're doing with it. And it's broadcast, so this information is out there available to everybody. And so the standards are there, and anybody can build an ADS-B receiver, just like anybody could build a GPS receiver. But now you don't have to, receive multiple satellites. You're just receiving information from the aircraft as far as to where it's positioned. There's going to be a corresponding standard or there probably already is a corresponding standard for V2V, vehicle-to-vehicle communication in ground vehicles, and V2I, vehicle to infrastructure, where the vehicle using its car using its GPS information can transmit that to other cars and can also transmit that to larger systems that are monitoring traffic. So anyway, for commercial transport category aircraft and for commercial general aviation, the Gulfstream aircraft and the like, those use 1090 extended Squitter ADS-B. There's another way to do this using what's called universal access transceiver, which operates on a different carrier frequency. I want to say 970 megahertz, if I remember correctly. And that's what's more frequently used by private general aircraft for ADS-B. Summary, we talked about Mode S or selective secondary surveillance radar, and that allows air traffic control to address individual aircraft. And so we saw the interrogation use what's called phase shift key. The response uses what's called pulse position modulation. We saw that there's a variety of interrogations that are available beyond just identity and altitude. And so the aircraft can respond to those interrogations, and it can also send those information out to other aircraft on a regular basis using extended Squitter. And then we used ADS-B is used as a implementation, is implemented for transport and commercial general aviation using 1090 extended Squitter technology. So that's sort of it for navigation and technologies related to navigation and surveillance. What we want to do next is start to move into sort of concepts of how do you get aircraft systems put together. So we need to talk about some systems engineering concepts and practices. And then after that, we're going to be moving through the rest of the semester. We'll talk about design for safety. How do we build, how do we design in redundancy, heterogeneity, dissimilarity, and the like to ensure safety. And then once we've able to talk about safety, we can talk about how do we get aircraft and software in aircraft and hardware in aircraft certified. And then we can talk about newer things like next gen and unmanned aircraft systems and unmanned aircraft systems traffic management, and then some other recent changes in the air transportation systems.